Alright guys, you have already taken the pre-quiz, so let's see how you guys did. Oil rig stands for oxidation is losing electrons, and reduction is gaining electrons. So if you can remember oil rig, you can know that if something is oxidized, it means it's losing electrons. If something is reduced, it is gaining. All right, to do oxidation numbers, let's practice. Oxygen is always a -2, making this a -6. That means that at the bottom I should have a +6 to total a 0, because there's a 0 overall charge out here. Since there are two S's, each one must be a +3. So when we're talking about oxidation numbers, it's the top numbers that I'm looking for, not the totals in the bottom. Here, oxygen is a -2, giving us a -6. N has to be a +5, because a +5 and a -6 gives me a -1. And since this is NO3 minus, that's going to be our charge for N, a +5. Over here, I've got O is a -2. I know that I have -8. I know that Cl minus is a -1, and I have two of those. That's a -2. And so over here, I have to have something. It's Ca is going to have to equal a minus, it looks like a 10. So this would be a +10. So let's take a look at that again. -8, and well, actually, I'm going to take this back. Let's go back to this one for a second. All right, this is ClO4, and there are two of them. So I know that calcium has to be a +2. All right, I know that O is going to be a -2. I know this is a +2. So here, this must be a -8. And I know that my Cl is going to need to be a +6, because 8 and -8 is a 0. So because I have two of them, each one of them should be a +3 for the Cl. Okay, let's do this one here. Na2O2. O is going to be a -2, have a -4. Na would have to be a +4, so at the bottom, so each Na would have to be a +2. All right, over here, -2, that would give me a -6 at the bottom. Over here, I know this is a +1 for sure. So here, it would have to be for the Cl a +5 to end up with a 0. Over here is a -2. I know that Cl is normally a -1, but in this example, Cl would have to be a total of a +2. So each Cl would be a +1. Over here, P2O5. So this one would be a -10, because O is a -2. That means this would have to be a +10, making each P a +5. Over here, Cl2 would just be a 0, because any element by itself is going to be a 0. Let's take a look here. Magnesium, Mg2+, and sulfur S2-. Which one is oxidized? Well, oxidation, if you look up top, is losing electrons. What would lose electrons? This one right here is oxidized. It would lose those two. And over here, S2- would gain 2 electrons, so that would be reduction. So which one is oxidized would be magnesium. Over here, lithium and chlorine, when they ionize, lithium is 1+, chlorine is 1-. They want to know which one is reduced. Reduction is gaining an electron. So this one here, Cl, would add an extra electron to become Cl-. Oxidation reduction reactions are called redox. Remember, they occur simultaneously, so the reduction and oxidation happen at the very same time. All right, to identify the oxidizing and reducing agent, we have to know what gets reduced and what gets oxidized. So the way we do that is we assign the oxidation numbers. So -2, -6, +1. That means that N has to be a plus 5. Over here, minus 1 plus 1. Remember, we don't worry about the coefficients at all, so you can just scratch those out totally. All right, here minus 2 plus 2, 0, all elements are 0, and then minus 2 plus 1 because this would be a plus 2. All right, so let's see what's happening. H stays the same, O stays the same, H the same. I goes from a minus to a 0, so I'm getting more positive. This is oxidized. That means it must be the reducing agent. N is going to go on this side from a plus 5 to a plus 2. So that must be reduction. I'm gaining electrons there, going from a plus 5 to a plus 2. And that means that's the oxidizing agent. So here, the oxidizing agent would be N, HNO3, the whole thing. And the reduction agent would be HI. Okay. All right, anox and red cat refers to at the anode, there's oxidation taking place, and at the cathode, there's reduction taking place. Electricity is the flow of electrons. The anode would be the negative terminal, and the cathode is always the positive. What you can always remember is that plus in cathode, meaning it's the positive terminal. What happens to the size of the electrode that undergoes oxidation and reduction? So we remembered fat cat, so that meant that the cathode was getting fat, and remember that that means the cathode gains mass, and remember cathodes are going to be reduced. So the cathode is getting reduced and it's gaining mass. That must mean that the anode is losing mass. All right, what directions do the electrons flow? They flow fat cat, so that means from the anode to the cathode. So I'm going to put on here from anode to cathode. All right, a voltaic cell is constructed in 1 molar solutions of lead 2 nitrate and gold nitrate using KCl as the salt bridge. Draw the cell. So I'm going to, just for fun, draw the gold on the left side, and I'll draw the lead on the right. So again, I have a 1 molar gold nitrate. Gold, it looks like here is 3 plus. So I would need to have AuNO3, and over here I would have 1 molar, and that was lead 2, so PbNO3 And so in the gold half cell, sorry you can't see this, in the gold half cell, I would need to have a gold electrode, so I'm just going to put Au, and in the lead half cell, I would need to have the lead electrode, Pb. All right, label the anode and cathode. So over here, I see lead written as a reduction and gold written as a reduction. So what I would do is I would come here and take a look at this reduction potential table. Whichever one is the highest gets reduced. So here's gold right here. And let's see if I can find lead 2 plus, lead 2 plus right here. So whatever is the highest is going to be reduced because this is the reduction potential table. So in a voltaic cell, whatever is the highest is reduced. So this is the highest. So lead is oxidized and gold is reduced. So this must be, since it's reduced, the cathode. And this, since it's oxidized, must be the anode. Again, whatever's the most positive on that reduction potential is going to be reduced. I'm also going to go ahead and write down the numbers here. So gold, since it was reduced, I'm going to write down exactly the way that it looks on the chart, 1.50 volts. So here is gold, exactly 1.50. But since the lead was oxidized, I'm going to need to flip this reaction and flip that sign. So positive 0.13. And so I'll put that down here. Positive 0.13. And again, I flip the sign because this is anode, and this one I left alone because it was the cathode. Okay, label the flow of electrons. So here's my wire, and here would be my salt bridge. So basically the flow of electrons goes across the wire, because remember metals are good conductors, and they flow from the anode to the cathode. So that means my electrons are flowing on the wire this way from the anode to the cathode. The standard cell potential, I flipped the sign for the oxidation. I left the reduction the way that it is. For the standard cell potential, you say 1.5 volts plus 0.13, and that's going to be 1.63 total volts. Again, it should be positive because all voltaic cells are spontaneous, and we should get a positive cell potential. All right, the overall balanced equation. So I had Au 3 plus, remember that's the cathode, plus 3 electrons going to solid Au, so I left that alone. But for the anode up here, I need to flip the reaction to show the electrons lost. So I would put here Pb solid goes to Pb2 plus and 2 electrons. So notice that since this is reduction, my electrons are on the reactant side, reduction reactants, and since this is oxidation, my electrons are on the product side because they're being lost. In order to do the overall cell reaction, those electron numbers have to total the same. I need it to be a number that's the same, so it's going to be 6 is the least common multiple. This equation has to be multiplied by 2, and this equation has to be multiplied by 3. So I'm going to go ahead and do that and add them together. So 2 Au3 plus 3 Pb. If I have 6 electrons here and 6 electrons here, they're out, so I'm going to leave those out. It's going to make 3, because my 3 here, 3 Pb2 plus 2 Au. And I want to make sure my numbers and my ions charges balance. So 2 Au, 2 Au, 3 Pb, 3 Pb, so my numbers balance. 2 times 3 is 6 plus. On the left-hand side, here's the reaction arrow. 3 times 2 is 6 plus. On the product side, we are balanced. So this is my balanced overall equation. And we did that. How many electrons were needed to balance? We needed a total of 6 because my 3 and my 2 had the least common multiple of 6. So 6 electrons balance this reaction. All right, let's take a look at a couple of different cell potential problems just to practice doing that again. So we'll take a look at this one first. It says, what's the standard potential of a cell made of Zn2 plus Zn and Ag1 plus and Ag? So let's see here. This is my Ag1 plus and Ag 0.8. And my Zn is going to be right here. So if they want to know what is the standard cell potential, remember that we take whatever is our highest number that is reduced. So that's going to be 0.8. And whatever is oxidized here, because it's lower, we need to flip the sign to a positive 0.76. And then I just need to add those together. So if we have a 0.8 plus 0.76, I get 1.56 volts. And the cool thing about that is it is a positive number, meaning that it is spontaneous, which means that I'm correct. If I got a negative cell potential and it was a voltaic cell, then something was wrong. Okay, last thing. A nickel electrode, so Ni 2 plus, and then copper 2 plus. So let's take a look at those two. Nickel 2 plus is right here. So I have nickel 2 plus here. And then we need to find the copper 2 plus. That's going from copper 2 plus to copper 1 plus. I don't want that. I want copper all the way to 0. So which one's higher? The copper's higher. So that's going to be my cathode. So it's going to be 0.34 volts plus. Remember, this one is lower, the nickel. So I need to reverse the sign, making it a positive 0.23 because we always change the sign for the oxidation, plus 0.23. And that gives us, a 0.57 total volts, which is going to give me a positive cell potential, making me understand that yes, this is correct because this is a voltaic cell and we should end up with a positive voltage.